Hello across the globe. My name is Matthew Fargo, and I'm the Senior Manager, Scientific Programs at the Royal Society. It is my distinct pleasure to welcome everyone to this first online discussion meeting held by the Society. Because of the coronavirus pandemic, we have more virtual offerings in the coming weeks and months ahead. So please do check our website and Twitter to see more about how we are continuing to engage the scientific community and the general public during these challenging times. The full meeting is rescheduled for the 20th and 21st of September 2021 and will either take place virtually or physically in London, and we hope the conditions will permit a physical meeting. Until then, you can view this coming video on the Society's website very soon. The selection process for the Royal Society's discussion meetings is competitive and is overseen by our Hook Committee. The proposal for the meeting on cracking, which we are about to begin, was amongst those considered to be most timely and meritorious. Cracks and cracking in materials is a ubiquitous and important topic, and this meeting will demonstrate some of the novel ways that researchers are looking at strengthening our future. I sincerely hope you enjoy the proceedings. Now we will hear from a member of the Royal Society's Council, Professor Julia Yeomans. Over to you, Julia.
Right, good morning, good afternoon, good evening, and welcome to everyone on behalf of the Council of the Royal Society. The Royal Society is steeped in history, and this is a historical day. Meetings in Oxford and London around 1660 resulted in the founding of the Royal Society of London and the beginning of over 350 years of discussion and science and innovation. Now in 2020, we, scientists from all over the world, are gathering using a technology that couldn't have been envisaged in the time of Charles II to hold the Royal Society's first online discussion meeting. Zoom isn't the same as meeting in person, and we all miss talking to friends and colleagues face to face. But I'm sure many of us regard one of the big advantages of being a scientist is to have so many friends and collaborators from all over the world. Zoom is going to make it easier to stay in touch. And this is particularly true for junior scientists and those working in economically underdeveloped countries where it's harder to find the funding needed to travel long distances. The Royal Society is committed to diversity, and Zoom will also open up our meetings to people who find it more difficult to travel because of family responsibilities or disabilities. And of course, any medium that reduces the carbon footprint of long distance flights has to have a big role to play in our future. Thank you very much to all the people who've worked so hard to find new ways of putting this meeting together. Have a cracking time learning about fracture, stranger than friction.
Hello and welcome. My name is Kendall, and I'm introducing this celebration of Griffith cracks. Here are cracks in glass that Griffith studied exactly 100 years ago this week. Welcome also to the Royal Society, the world's oldest running scientific community. One of our early presidents, Isaac Newton, did study cracks himself, but not very successfully. He wrote papers in the Philosophical Transactions, the most ancient scientific magazine on the planet. And that is where today's papers will be published next year. This is the front page of the first volume of Phil Trans. Remember, this came out in the plague year 1665, when many scientists had left the cities to avoid people dying in the streets. Newton himself went home to his farm and did his greatest work there under lockdown. Griffith's famous paper was printed in January 1921, Phil Trans, originally being presented in October 1920. In it, Griffith produced his famous equation from the conservation of energy principle, which seemed crazy at that time. He showed that the stress at crack equilibrium, sigma, went down predictably as the crack length c went up. And this required the new idea of toughness, W, the fracture surface energy, which is the energy needed to separate atoms against the atomic attractions as the crack proceeds. Now the problem is that millions of engineers still use the old Galilean pressure theory of strength. What Galileo did was test a ceramic sample, applying a force with this weight and causing a crack here. He postulated that stress Now this force divided by cross-section area dictated cracking. Today, we want to get it right once and for all. First, we want to celebrate Griffith's contribution. Then we want to present new results and theories like graphene reinforcing cement. And finally, we must reject the errors in fracture mechanics. It's a subject riddled with defects. The first speaker is Anga Teresa Kono from the United States to talk about graphene toughening cement. Siva Bohm has worked for many years on the manufacture of graphene. He takes a block of graphite, splits it into billions of atomic layers. You see, graphene is made by a cracking process. Then Rob Ritchie distinguishes between toughness and strength, followed by Alan Roberts, who's famous for discovering cracks between two adhering rubber spheres. And that's narrated by Pyle Behetty. Then Kendall, our younger speaker, has done calculations during lockdown of compact tensile tests for lab studies. Finally, Irene Fernandez-Villegas reports interesting results on welded thermoplastic composite sheets for aircraft. These sheets could crack along the weld to cause a disaster. A new approach to this problem is urgently needed because the ASTM standard does not mention Griffith. I will then summarise the meeting conclusions and look forward to the rescheduled London conference in 2021. Please send in your questions for the discussion sessions. And now, here is the first paper from Professor Okono.
Hi. Today I'm going to be presenting on fracture toughness of 1D and 2D nano-reinforced cement via scratch testing. The research motivation is the need to reduce the carbon footprint of the cement industry. The cement industry accounts for 7% of CO2 emission globally. Now, one part of it is going to come throughout the synthesis of cement as we need to heat raw materials to a very high temperature. Another part will come throughout the lifetime of buildings and structures as we need to continually heat and cool down buildings. One way to reduce the carbon footprint of cement is going to be to design high-performance cement nanocomposite. That way, when there's a given project, we can significantly reduce the volume of cement needed to be able to complete the project. And what I'm going to be showing today is that nanomaterial enable, in particular, to enhance the mechanical properties and also enhance the durability of cement nanocomposite. There's a wide range of nanomaterial, and today I'm going to be focusing on 4 types of carbon-based nanomaterials: graphene nanoplatelets, helical carbon nanotube, multi-wall carbon nanotubes, and carbon nanofibers. In terms of dimension, the thickness of the graphene nanoplatelets is 8 to 15 nanometers. The diameter of the helical carbon nanotube and multi-wall carbon nanotubes is 20 to 50 nanometer. The diameter of the carbon nanofibers is 150 nanometers. In terms of length, the dimension of the graphene nanoplatelets is 1 to 2 micron. The length of the multi-wall carbon nanotube and helical carbon nanotubes is around 50 micrometers, and the length of the carbon nanofibers is between 50 to 200 micrometers. Despite a lot of studies focused on the topic, some open questions involve the influence of carbon-based nanomaterial on the microstructure of cement and the influence of carbon-based nanomaterials on the mechanical properties. In this talk, I'm going to be using the fracture toughness as a criterion to evaluate the mechanical performance of cement nanocomposite. I will look at 3 types of reinforcement level: 0.1%, 0.2%, and 0.5%. 0.1% and below has been extensively studied because then it is easier to disperse nanomaterials. 0.2% and 0.5% are interesting when we want to be able to design sensors for structural health monitoring, for instance. However, they are challenging in terms of synthesis. And I'm going to be tackling this. So in terms of experimental programs, first I'm going to be showing how I'm actually able to yield my cement nanocomposite. Then I'm going to be probing the microstructure and the mechanical properties. And finally, I'm going to be concluding. Now, when it comes to the synthesis, the important question is, how do we achieve a uniform dispersion of the nanomaterials? How are you able to make sure that they are not going to become clustered within cement matrices? So for me, I'm going to be using a series of steps. So first of all, I predispose the nanomaterials within using deionized water and ultrasonic energy. Then I'm going to be able to mix that suspension using high speed and high shear and mixing it with cement powder. Afterward, I'm going to be casting it and using, in this case, mechanical stirring during the first 24 hours with an orbital shaker. And then I'm going to be curing for 6 days using deionized water. So let's look at an example with carbon nanofiber reinforced cement. So first I'm going to be weighing the carbon nanofibers, and I'm going to be weighing the deionized water. Then I use ultrasonic energy to predisperse the carbon nanofiber. Now that dispersion is not optimal. So this is why in the second step, I'm going to be using high speed and high shear and cement powders. So this time the unhydrated cement grains are going to help me further disperse the carbon nanofibers. And then after pouring the slurry, I'm going to be using an orbital shaker. And with mechanical stirring, I will keep breaking any potential clusters of carbon nanofibers so that I obtain at the end a uniform and well-mixed carbon nanofiber cement composite. So I'm going to be testing the mechanical behavior using scratch test experiment. In my test, I use a Rockwell tape, that is a spheroconical probe, and I'm going to be prescribing the vertical force while recording the horizontal force and the penetration depth. Some traditional application of scratch testing involve, in this case, addition and cohesion of thin film and coatings, strength and hardness of ceramics, strength of rocks, wear of polymers, and damage of metals. What I did was to design a nonlinear fracture mechanics model to be able to relate, on the one hand, the forces to the geometry and to the fracture toughness when it comes to scratch testing. So the final equation is given over here, and that is going to relate the horizontal force to the geometry and to the fracture toughness during scratch testing. So then I have a methodology, and let's move forward and let's look at the result. The first question I ask is, how do nanomaterial influence the microstructure when we have graphene nanoplatelet cement, for instance, when we have helical meltawell carbon nanotube reinforcing cement, meltawell carbon nanotube, or in this case, carbon nanofibers? And overall, what I observed is that there were a reduction in the microporosity, both in the quantity and in the size of the pore, meaning that nanomaterial tend to densify the microstructure of cement matrices. Then I use high-resolution scanning electron microscopy to understand how nanomaterial interact with cement hydration products. And I looked at graphene cement, I looked at helical carbon nanotube cement, meltawell carbon nanotube cement, and carbon nanofiber. And what I saw is that nanomaterial tend to bridge nanoscale air voids and connect cement hydration products. So after conducting my scratch test, I then use a scanning electron microscope to image the residual groove after scratch testing. One thing that I noticed was the presence of microfracture on the surface of those residual grooves, and those fracture surfaces were perpendicular to the direction of scratch testing. This means that during scratch test, we are activating fracture processes, and therefore we can use the test to be able to probe the fracture resistance. I identified 4 types of fracture micromechanisms: microcracking, crack deflection, ligament bridging, and debris formation. We can even see the thickness, in this case, or the width of the crack during the fracture, and it is between 1,000 to 2,000 nanometers. So then I use my model to be able to assess the influence of nanomaterial on the fracture toughness. Now, according to my model, this quantity should be constant. And what I saw is that for very low values of the penetration depth, there's actually a mix of both ductile and brittle deformation taking place. However, when we go to very large penetration depth, then brittle failure becomes dominant, and in that range, we can then measure the fracture toughness. Then I try to see what is the influence of both the type of nanomaterial and their volume fraction on the fracture toughness. Now, for graphene nanoplatelets, I observe always an improvement in the fracture properties, in the fracture toughness, when we add graphene nanoplatelets. Similarly, for carbon nanofibers, there's always an improvement. However, in the case of helical carbon nanotube and meltawell carbon nanotube, there are some volume fraction where we observe a slight decrease, a really small decrease, and that suggests that there's some room to optimize our dispersion process. One thing that is very remarkable is that when it comes to 0.5%, for all 4 types of carbon-based nanomaterial, we have a 10% increase in the fracture toughness. So this means that the procedure that I presented is really important and enable to significantly improve the fracture toughness of cement nanocomposite. So in conclusion, I've shown that nanomaterial yield a decrease in the microporosity and in the size of micropores within Portland cement. I've shown that nanomaterials bridge nanoscale air voids. I've shown that scratch tests can be used to probe the fracture toughness of Portland cement. And in the case of cement reinforced with 0.5% of nanomaterials, we see an improvement in the fracture toughness by up to 10%. Thank you very much.
Thank you very much, Angie, for that really fascinating talk. I'm Tony Kinloch from Imperial College London, and I'm going to be moderating the session. And please send your questions in via text message using the Slido app, either to an individual speaker and also for the general panel discussion later in the morning. That's a really fascinating talk. Thanks, Angie. A very different type of material as well. Several questions have come in. If I can ask the first one, your crack test is very interesting. Have you compared the results that you obtained with those from more standard fracture tests, such as bending tests?
That's an excellent question, Professor Kinloch. So what we did actually is to compare the result of scratch testing with 3-point bending tests. This is currently the ASTM standard when it comes to fracture characterization. And I use both homogeneous, and I focus on homogeneous material. So for instance, for steel, we observe that we have an agreement for steel 1144. And the same way that we also had for polymers, for instance, I look at polycarbonate, and I also look at paraffin wax. So this means that our method is actually valid and enables us to prove the fracture toughness at the microscopic lab scale.
Thanks very much. Lots of questions. Just try and choose some of these. Asked from Etienne Bartel, in terms of application, cement's a relatively low cost material. What's the added cost for producing the material when you reinforce it with these much more expensive carbon nanomaterials?
That's a very good point. There's going to be some increase in cost when we add the nanomaterial. The key point is we use really small volume fraction. So for instance, what I showed is when you add only 0.5% per weight of cement of carbon nanomaterials such as graphene, you can increase the fracture toughness up to 10%. You have to understand that cement is very weak, especially when it comes to fracture, and it tends to break very, very easily. And this leads to durability issues because we need constantly to be able to repair. So I think that the added cost is actually compensated by the increase in performance that we obtain by incorporating only very tiny volume fraction of nanomaterials in this case.
And another one from Dougal Goodman, who asks, are there health risks associated with the fibers?
Not that we know of. No, it should be very, very harmless. Yeah.
All right, thank you very much. We'll have time for more questions in the panel discussion at the end. So please ask other questions as well, we'll come back to. And now we move to the next talk, which is Siva.
I am Siva Bohm and currently affiliated as Industrial Graphene Research Scientist and Royal Society Industry Fellow at Imperial College London. I'll be speaking about graphene production by cracking. Graphite is a joint covalent substance in which each carbon atom is joined to 3 other carbon atoms by covalent bonds. The carbon atoms form hexagonal layered network structure. Each carbon atom has one non-bonding outer electron. The layers stuck together with van der Waals forces acting between them. The forces between the layers are weak, therefore they can slide over each other, giving rise to the lubricity of graphite. Non-bonding electrons are delocalized, are free to move through the structure of graphite so that graphite can conduct electricity. This makes it useful electrodes in batteries and electrolyzers. Technically, graphene structures resemble a single layer of graphite. Graphene, therefore two-dimensional crystalline form of carbon, has attracted wide and intense interest owing to its excellent physical properties and because its surface and edges can be chemically modified readily. The delocalized electron on a single layer graphene is even more conductive. Graphene production from graphite via top-down route has many unique advantages and is based on the one-step physical transformation of graphite into graphene. However, pristine graphene production has been pursued with difficulties either in production rate or in number of layers present in each graphene platelets. Liquid phase exfoliation from graphite to graphene require input energy to overcome forces between the layer. The required energy is provided by various means such as sonication or electrochemical energy or mechanical energy or high pressure to break existing interlayer interactions. Besides many molecules such as surfactant molecules and polymer compounds as exfoliation agents are used to generate new forces such as 5-pi conjugation, hydrophobic force and Coulomb attraction, and match the surface energy of the graphene layers to that exfoliation media. The underlying scientific principle is similar to Griffith theory of crack propagation. Reduction in potential energy should be greater than or equal to an increased surface energy due to the creation of a new free surface. The excess energy exerted by the chosen exfoliation technique can also fragment large graphite particle or graphene layer into smaller ones. The fragmentation effect has double phase tactics. On the one hand, it can reduce the lateral size of graphene. This is not desirable for achieving large area graphene. On the other hand, it facilitates exfoliation because smaller graphite flakes are easier to exfoliate than larger ones because of the smaller collective van der Waals interaction forces between the layers in smaller graphite flakes. The energy calculation for separating the graphene sheet from graphite and dispersing in the solvent can be done as follows. The enthalpy of mixing for graphite in the solvent should be equal to the energy required to separate all molecules, solvent graphene sheet, to infinity, minus the energy to bring them back together in the form of solvent graphite dispersion, but with the flakes of different thickness, where the specific enthalpy change is proportional to the square root of the surface energy difference between the graphene and the solvent and inversely proportional to the flake thickness. The most commonly used top-down method for producing graphene from graphite suffer from quality versus quantity trade-off. There are two methods producing graphene from graphite in large quantity. The often used modified Hamas process involves extensive oxidation. Still, the resulting graphene oxide can be thermally or chemically reduced to yield reduced graphene oxide nanosheets that retain some of the defects and oxygen-containing functional group. In contrast, pristine graphene is exfoliated from graphite, often its liquid medium, with sonication or electrochemical or high-pressure exfoliation. Raman spectroscopy is the useful technique for characterizing sp2 and sp3 hybridized carbon atoms, including graphite and graphene and other carbon isotopes. 2D band is a second order of 2 phonon process and exhibits a frequency dependence on the excitation of laser energy. The 2D band can be used to determine the number of layers of graphene. And the 2D band is the single layer is much more intense and sharper as compared to the 2D band multi-layer graphene. The samples which has been produced, the spectrum shows the high contents of monolayer graphene as indicated by the symmetrical 2D peak with a Lorentzian profile centered 2680. The low D peak suggests that the graphene has low defects. HRTEM and the electron diffraction spots are labeled using Miller's Bravis indices. The ratio of identified peak intensity 0 order and first order spots is indicative of single layer or bilayer of graphene on the area of under electron beam. Graphene-enhanced lithium-ion batteries shown incredible characteristics such as long lifespan, high capacity, faster charging time, and lightness. Fuel cells are considered the 21st century technology for the production of electric energy. This is due to its high efficiency, low emission, safety, and silence. New catalysts can increase the conversion efficiency of fuels, increase the durability, and decrease the cost. Anti-corrosion coating with graphene, reduced graphene oxide, nanoplatelets have been evaluated and promising for protective coatings. Graphene is called wonder material or ultimate additive for a reason. There are many industrial research which are not published yet, but may change the world tomorrow. Thank you for your attention.
Thanks, Siva. Your exfoliation methods is really fascinating. One question that's come in is from Fyodor Borovich. Carbon nanotubes and graphene are rather inert. He points out that they usually do not create chemical bonds with surrounding materials. And how will you resolve this problem?
Sorry. Yes, the dispersion of the, hi, thank you, Professor Kinloch. Thank you, Professor Kinloch. Thank you for the questions from the audience. It's the nanomaterials to how do you disperse them? How do you functionalize them? How do you keep it into the form that they can incorporate it into appropriate products? That is the key, and that is mastering the technology. How do we manipulate the product in order to achieve the expected functionality?
One from Mark Guessing. Once separated, what prevents the graphene from recrystallizing into new graphite crystals?
It simply is a forces what steric repulsions. We are introducing either molecules which can keep apart from each other, and or we can make it functional groups, which is building blocks like puzzles in children's. They build together, like we can put the figures. How do we want it to interconnect the chemical? The edge bonding, edge functionalization is the key. How do we build the molecules that they are not attracting each other, because we have introduced already some additives to keep them apart each other.
Thank you very much, Siva. I think to keep us on time, we should move on. And the next talk is going to be from Rob Ritchie. Rob.
Hi, my name is Robert Ritchie from the University of California in Berkeley, and I want to talk about toughness today. So toughness is often confused with strength, but they mean very different things. Strength is generally resistance to deformation, plastic deformation, but toughness is resistance to fracture. Now, these two terms, unfortunately, are often mutually exclusive. If you look at this Ashby plot of the fracture toughness function of yield stress, you can see that for each class of materials, metals, polymers, and ceramics, that there's often an inverse relationship between toughness and strength. And so we really have to, when we generate a structural material, we really have to get both those properties. So that's often an exercise in compromise. Now, why is this? Well, toughness is often a mutual competition itself. Toughness is resistance to damage in the materials, and that's what I call intrinsic toughening. This takes place generally ahead of the crack tip. Damage is in the form of breaking particles, cracking the matrix, causing decohesion, and it's generally resisted by plastic deformation or plasticity or whatever form of inelastic deformation you have. This is the main source of toughness in metals, and it occurs ahead of the crack tip. But you can't use that very readily for ceramics. Ceramics tend to be toughened by a different mechanism, totally different mechanisms, which involve shielding the crack tip from the applied driving forces. And these are mechanisms that operate at and generally behind the crack tip. They're associated with bridging, say, fibers or grains that would carry load that would otherwise use to propagate the crack. There's a grain bridging zone in a ceramic silicon carbide. These mechanisms operate basically in multiple length scales, whereas plasticity is generally generated at the nanoscale. So these, the intrinsic ones ahead of the crack tip for ductile materials, primarily extrinsic ones behind the crack tip, primarily for brittle materials. But biological materials seem to be able to combine both these mechanisms quite readily, and they do that by having multiple length scales in their microstructures. This is bone. It has characteristic dimensions at the nanoscale, twisted peptide chains, mineralized collagen fibrils, all the way up to the osteonal structure and the bone itself. So if you look at the mechanisms of toughening in bone, they combine both intrinsic and extrinsic. At the small scales, for example, below a micron, ahead of the crack tip, you see intrinsic toughening from plasticity. Plasticity in bone is generally many mechanisms, but generally it's the stretching of the collagen fibrils and then them sliding apart. That's fibrillar sliding. Anything that inhibits that will tend to inhibit plasticity. If you look above a micron behind the crack tip, you see all the extrinsic mechanisms that you might see in a ceramic. Microcracking, bridging by collagen fibrils, little regions between the microcracks that act as bridges, and deflection at the collagen fibrils. I have a few images of this from tomography. These are the osteonal structures or bursting canals, and you see the crack deflects and twists as it encounters those structures. If we look in the other orientation, you can see there are the osteons again. This white region here is the crack. There's the head of the crack, and these dark blue regions are these uncracked ligaments, which are these little regions between the microcracks which act to bridge the material. Now, if we look at other biological materials, some of them are intrinsically toughened. Skin is a good example. It's collagen again, but non-mineralized collagen, just pure collagenous materials. Skin is virtually impossible to actually break. You do a tear test on it and it just won't break. It generates blunts or cracks and so forth. Now, how does that work? Well, it consists of a tangled mass of collagen. These collagen fibers are very twisted and curved. And what happens when you put a load on skin? These collagen fibrils tend to straighten, and then they tend to rotate to carry more of the load. They then get into a they've straightened and they get into this sort of a line situation, much like a polymer might, and then they sort of stretch themselves, they separate and delaminate, and they finally fail. So you start off with a tangled mass of a curvy collagen, and you end up with these aligned ones, which are really very effective in absorbing energy. Now, the other extreme is a ceramic, which is purely extrinsic. This is a silicon carbide reinforced with silicon carbide ceramic. These are materials that are now being put into jet engines by Rolls-Royce and Pratt & Whitney and GE. This is a particularly high temperature version. This is a tensile test that we're doing in the synchrotron at a ridiculously high temperature of 750 degrees C, and we can do the tensile test and see what's happening at the same time. You see a crack development here, and you can see the bridging by the silicon carbide fibers. These are very important. To enable the crack to be bridged by them, you have to have a weak interface, and they're coated by boron nitride to remain such that they can slide and generate bridging. Now, the other extreme from the pure ceramic is the pure metal, and this is metals. This is toughening by in high entropy alloys, metallic materials. This is purely intrinsic. These are fascinating materials. They have multiple principal elements. They often are single phase. This one's a cobalt, chrome, nickel, single phase alloy. These are the tensile tests at room temperature in brown. When we go to low temperatures, liquid nitrogen temperatures in blue, you can see that they get stronger at lower temperatures. Well, that's predictable, but they also get more ductile, which is highly unpredictable. In fact, the properties of this material at liquid nitrogen temperatures have 90% tensile ductility at 1.3 gigapascal strength, which is remarkable. We do a toughness test on these. These are called R curves, JR curves in fact, and the toughness of these materials at liquid nitrogen temperatures is almost 300 megapascal root meters. Now, typical aluminum alloy would be 30 megapascal root meters. Silicon is 1 megapascal root meter, so these are really tough materials, and in fact, in their crack growth toughness is as high as 450 megapascal root meters, which is a mind-boggling number. How is this achieved? It's achieved through steady strain hardening, which hardens the material but the strain hardening delays necking, so you generate ductility. So there's mechanisms here, deformation mechanisms that promote ductility and in strength, the duality of function by a synergy of deformation mechanisms. You can see a few here. This particular structure forms a hierarchical twin structure. The twin boundaries act to arrest dislocations that impinge on them. That is the hardening mechanism. But by the same token, these same boundaries actually act as highways for the dislocations to move. Those are the ductility mechanisms. So we have means basically of generating strength and ductility by separate deformation mechanisms, a synergy of deformation mechanisms to generate a duality of function, which leads to this very high strain hardening. Let me conclude by saying I've looked at how metals are toughened by intrinsically, how ductile materials are toughened intrinsically. Brittle materials like ceramics are extrinsically. The latter is associated with shielding behind the crack tip primarily, but the intrinsic ones associated with plasticity ahead of the crack tip. But biological materials have this interesting function that they have multiple length scales. These different mechanisms are formed at different length scales, and so biological materials tend to be able to generate both intrinsic and extrinsic toughness, which gives them their remarkable properties. Thank you very much.
Hi, Rob. Thanks for your excellent overview talk, as always. Immediate question from actually Kevin, our chairman. He says, great results in your silicon carbide composites. When you say weak interfaces, do you really mean brittle interfaces?
Yes, I mean, the term is generally used as weak, but the notion is you need the fiber to be able to move with respect to the matrix. If it was tightly bonded to the matrix, the fiber would break when the matrix breaks, and you would lose the absolutely critical property of these materials, that they have some form of ductility, because they will basically yield when the matrix breaks, but the fiber then holds it together until the ultimate strength when the fibers break. So you've never used them in those regions, but that fiber bridging is absolutely critical, and it's associated with the ability of the fiber to move relative to the matrix to pull out the classic toughening mechanism of composites. But Kevin's right, they really are brittle. It's a fracture problem rather than a strength problem, but people refer to them as weak interfaces.
A question from Alois Ivankovic, University College Dublin. He points out, of course, that ceramics have a high modulus. So when you convert K1C into G1C, you end up with a very small number. Would you care to comment on that?
Yeah, that's a funny thing. If you actually rank materials in terms of their energetic toughness versus their stress intensity toughness, you do get seemingly anomalies like that just because of the modulus situation. And it depends on how you design the material. If you design it to withstanding a certain stress in the presence of a crack, then maybe a K-based approach is better. But there are other situations where an energetic approach is better. But that is just that's the nature of the game. There is that seemingly anomaly because of the modulus.
Thank you very much, Rob. I'm sure we'll come back to these points at the end during the general discussion panel. Thanks very much indeed. We now move to Payal's talk.
Alan Roberts is unfortunately not available today, but he'll be in London next year at Royal Society meeting to chair the session on JKR cracks. So I'm Payal Baheti, delivering his script and slides on smooth rubber adhesion cracks. Let me take you back in time, not 100 years to Griffith, but 50 years to 1970, when Alan was working on rubber windscreen wipers in his PhD project to make better wipers. Here is a windscreen wiper on wet glass and it doesn't stick. But on clean dry glass, it can stick remarkably well. You've probably experienced this in your car when the windscreen dries out and the wiper motor stalls. One of the first problems Alan addressed was the variable roughness of commercial windscreen wipers. This made the contact between rubber and glass quite changeable. Therefore, Alan invented a way to mold the hot rubber in a glass concave lens to get an optically smooth and reproducible surface every time. he took a wedge of raw rubber and inserted it into a smooth glass former, then hot pressed it to crustling the polymer so it went solid. This improved the contact experiments immensely, and Allen could see the interference fringes clearly through the microscope, thereby measuring the contact area very accurately. That was the cause of the Eureka moment in 1966, when Allen first saw that the contact of the dry rubber on glass was much bigger than that on the wet glass. This black spot is the dry contact of smooth rubber on glass. Then in soapy water, the spot size was much smaller. The result at the different contact forces, that is, the contact size on the vertical axis, windscreen wipers force on the horizontal, showed that the wet rubber fitted the elastic deformation theory, whereas the dry contact gave much bigger contact area. This big discrepancy seemed to Allen to be the effect of van der Waals force attracting the rubber to the dry glass. Because the point contact is much easier experimentally than a long windscreen wiper, and also because the Hertz elastic contact theory is for sphere contacts. Allen began to mold optically smooth rubber spheres to compare directly with the well-known Hertz equation from 1882. The sphere radius r, the applied force F, and the Young's modulus E. Then the experiment could be plotted with the famous equation that Hertz found during his Christmas vacation while he was a university student. The diameter 2r of the black contact spot was readily measured in the optical microscope apparatus. You can see some small white defects here, but most of the area they are in perfect contact. From this plot of theory versus the experimental results, the soapy water contact radii fitted the Hertz cubic theory very well. There was no adhesion there. But the dry black spots, they were much bigger, and a tensile force was needed to pull them apart. The conclusion was that the discrepancy in the dry results was a definite measure of van der Waals force. But how can you produce a theory to explain that? Ken Johnson was the brilliant stress analysis engineer who had obtained the stress-filled solution much earlier by adding two well-known stress distributions in 1958. Sadly, he died in 2015, famous for his contact equations and his book on contact mechanics. Without Ken, it would not have been possible to explain this adhesion crack. This is the Hertz 1882 pressure distribution for zero adhesion. Here is the Bossinus pressure distribution from 1885 for adhesion between a cylindrical punch and an elastic material. Ken added these two stress distributions together and then observed the infinite stress at the edge of the combined contact, but failed to consider the Griffith energy argument to analyze the equilibrium. He presumed that the stress analysis was sufficient to solve the problem. No, it is not. It was 1970, 12 years later, when Kendall realized that it was necessary to apply Griffith's energy balance. Many stress experts still think that stress causes failure. No, it is the conservation of energy that prevails. The energy balance worked out by Ken Johnson on Cup final afternoon in 1970 showed that the Hertz equation needed 3 more terms to fit the results, as shown in this equation and this graph. There were some problems getting to equilibrium because the crack slowed down as the rubber contact peeled apart, but the fit was reasonable. Every day, this paper is cited by international research groups working on many different fields, from accretion of cosmic dust to handling powders in chemical industry to virus nanoparticles adhesion to the design of sneakers for athletes. Interest was slow at first during the 1970s to 1980s, but then accelerated rapidly. In conclusion, the Hertz equation of contact needs more terms when van der Waals attractions cause smooth surfaces to stick together. There is no crack in the Hertz theory, but there is a crack in the Bosonesque solution, which must be added to account for the van der Waals attractions. This story shows that stress analysis in itself cannot give the condition for cracking. Stress theoretically goes to infinity at the crack tip. The stress distribution must be used to work out the energy balance argument that Griffith invented in 1920. Then the new JKR equation emerges, fitting the experimental results for equilibrium. The main message is that stress itself does not define crack equilibrium. Energy does. Finally, congratulations to Alan Roberts on the wonderful invention and discovery.
Thank you very much indeed. Thank you. An excellent talk. Thank you very much indeed for giving it. Now we move on to Khan.
My name's Kendall and I've been locked down in summer, so I did a project on calculations of cracking in this compact disc test sample. The diameter is D and edge crack is length C. F is the applied force. The Griffith equation had three major problems. First, it assumed an infinite sample. Then, it had a central crack. Third, it assumed uniform tensile stress, which is difficult experimentally. Amazingly, it took more than 50 years to obtain the edge crack equation here. This requires 11% less force for fractures than Griffith's, so it's more dangerous. Then 6 years later, Gregory produced his exact equation for a lab crack test on discs. Ronald Douglas Gregory was a mathematician at Manchester University who used the energy conservation principle to get this unique equation, published in Cambridge Philosophical Society in 1979. This is a Griffith-like term, while this is a bending term. The nominal strength is F over BD, and I've been calculating the strength for perspex discs, which are known to crack very controllably, so we can test this experimentally later. First, I calculated the crack equilibrium force for axial loading. The force F is applied along the diameter. The Griffith curve does not fit the facts, and the edge crack solution also does not fit. Here is the nominal strength F over BD, and here is the disc diameter. Meanwhile, the Galileo idea that force is proportional to the area is totally wrong. The Gregory strength goes to 0 when the crack has crossed the disc, which makes sense. The most interesting result is for off-axis loading. Here, we had to take into account the distance A, the distance of the force application from the edge of the disc. This calculation shows very interesting new behaviour. First, the strength falls below the axial curve. The sample is weaker in off-axis loading. But the most interesting change is that small cracks now behave differently. The force is 0 for a 0 crack length, whereas Griffith's force goes to infinity. This gives a size effect in which the disc gets weaker as it gets bigger, using equal crack lengths. But such size effects exist in bending cracks, compressive cracks, and adhesive joint cracks. Moreover, the Gregory curve fits Griffith's original results on strength of fine glass fibres. Griffith, in 1920, melted glass and pulled it to form fine fibres of several diameters. He got results showing fine fibres were stronger, but could not explain it with his cracking equation on infinite sheets under uniform tension. In conclusion, these calculations show that Gregory's equation is more interesting than previously thought. It beats Griffith's because it uses a finite sample and uniform stress isn't needed. The actual loading gives a result like Griffith's, but better, because the force must go to 0 when the crack reaches the end of the disc diameter. Off-axis loads introduce bending, which gives a size effect. The disc gets weaker when it is bigger. Remarkably, the equation even fits Griffith's original 1920 results on glass fibres. Fine fibres are stronger. Now, I want to go to the lab and get experimental results. Thank you for your attention.
Thank you very much, Khan. Extremely well presented, very clear, and your calculations are really interesting. I guess the basic question is, what calculation method did you use, please, for getting your results? Excel spreadsheet, Mathematica, and maybe you could add a comment on that, please.
Yeah, so I used Excel, and also I used a graphical, a graph plotting program, so I could look at the different equations.
And when you get to the lab, when you observe these cracks in polymethyl methacrylate, better known as perspex or plexiglass, how are you going to measure the crack length? Have you got some techniques in mind there, please?
Well, you can draw a line from where the crack starts and then move the crack until it finishes, and then draw another line and measure the length there.
Right. Well, good luck, and hope lockdown finishes soon. You can get back and do the experiments and come back and tell us what they're like next year at the meeting. Look forward to that very much. Thanks again, Carl.
Thank you very much.
Right. Thank you very much indeed. Now we go to Irene.
In this short video, I would like to talk about the dangers of single lab shear testing in understanding polymer composite welded joints. My name is Irene Fernandez Villegas. I work at the Delft University of Technology, and my research has focused on composite welding processes and welded joints for the last 15 years. First of all, some basics about welding of polymer composites. Welding, also known as fusion bonding, is a group of joining technologies in which the surfaces of two matching parts are joined together through simultaneous application of local heat and pressure. The bonding mechanism is interdiffusion of the polymer chains across the welding interface, similarly to a polymer healing process. The different welding techniques are often classified based on the physical phenomenon by which heat is generated at the welding interface. Hence, we have electromagnetic technologies such as resistance or induction welding, vibration technologies such as ultrasonic welding, and conduction technologies such as hot tool or laser welding, to name a few. Welding is most commonly applied to thermoplastic composites, but as shown by recent research, it can be used to weld thermoset composites as well. In composite welding, we often use single lab shear testing to quantify the quality of welded joints in order to develop welding processes or to compare different welding approaches. Why single lab shear testing? Well, single lab coupons are easy to manufacture and to test. Moreover, the test provides information about shear behavior, which is especially relevant for bonded joints. Particularly, the ease of manufacturing plays a big role when it comes to welding, since owing to their local heat generation, welding processes are highly sensitive to heat transfer and hence boundary conditions. Take for instance the case of a double lap welded joint. One way of producing it would be by welding a single lap joint first, and then welding a third adherent to it. However, if we consider the heat transfer problem, we can see that the first and second welds have different boundary conditions. Hence, we will most likely need different welding parameters to achieve the same weld quality in both cases. This is illustrated by these fracture surfaces that indicate quite different failure behavior when the same welding parameters were used to obtain the two welds in double lap joint. We should, however, be aware that the single lap shear test has some particularities. Firstly, the joint is not subjected to pure shear, but to a combination of shear and peel stresses. Secondly, the stress distribution at the joint is not uniform, but it features a so-called bathtub shape, with peak stresses at the edges of the overlap. Finally, these peak stresses are sensitive to numerous factors such as bond line thickness, whether the adherents are tapered or not, the presence of fillets, or the stiffness ratio between bond line and adherents. Despite these particularities, the single lab shear test is commonly regarded as a useful tool for comparison and process development. Let's see how that works for composite welded joints. First, an ambitious comparison, welded versus mechanically fastened joints. In this study, we followed a stepwise approach in which first we looked separately at the shear and peel behavior of the two types of joints. The welded joint consisting of a 10 mm diameter ultrasonically welded spot and the fastened joint of a single high-lock fastener. The shear performance of both types of joints was similar. However, the peel load carrying capability of the welded joint was 5 to 6 times lower than that of the fastened joint. Based on these results, we expected the single lap shear strength of the welded joints to be significantly lower than that of the fastened joints. But fortunately for us, that was not the case. But why? Well, if we go back to the shear tests, we see that the welded joints had a much higher stiffness. Consequently, secondary bending during single lab shear testing was lower, which resulted in lower peel and hence a more favorable stress scenario at each load level in the welded joints. Can we say this was a fair comparison? Let's look now at the comparison among different welding processes. In this second study, we used single lab shear testing to compare among ultrasonic resistance and induction welding. The tests indicated that induction and ultrasonic welds behaved similarly and were somewhat stronger than resistance welds under static loading. Additionally, there wasn't any significant difference in behavior under dynamic loading. However, by examining the cross-sections of the three types of joints, we saw, firstly, that in resistance welds, the weld line, which is indicated by the white arrows, was fundamentally different from the weld lines in induction and ultrasonic welding, in the sense that it contained an embedded resistive element, which is responsible for heat generation, in this case a metal mesh. Hence, the presence of the resistive element resulted in a different thickness and probably stiffness of the weld line in resistance welds. Secondly, that the typical occurrence of through-the-thickness heating in induction welding plus the application of the welding pressure resulted in tapered adherence. From these two observations, one could imagine that at the same load level during the single lab shear test, the stresses developed in the ultrasonic resistance and induction welds were not the same. So we come back to the same question. Was this a fair comparison? Finally, let's look at the role of single lab shear testing in the optimization of a welding process by investigating how changes in different process parameters affect the quality of the welded joints. In this particular graph, we see the single lab shear strength of ultrasonically welded joints obtained at different vibration times. Let's first focus on the first region of the graph, where the single lab shear strength increased with increased vibration time. If we look at the fracture surfaces of the joints welded in this region, we see that the welding process started at the edges of the overlap and progressed towards the center. Hence, as the vibration time increased, so did the amount of welded area and the single lab shear strength. Based on this trend, one could expect to find no changes in the amount of welded area in the second region of the graph, where the single lab shear strength remained constant. However, the fracture surfaces showed otherwise, indicating that after a certain threshold, the single lab shear strength values did not allow us to discriminate anymore between partial and fully welded overlaps. We believe this is due to the stress distribution during the single lab shear test, in particular the fact that the stresses are much higher at the edges than anywhere else in the overlap. Therefore, the quality of the weld at the edges of the overlap can be expected to contribute more towards the final strength value than the quality of the weld in the center. After all my years of experience working with polymer composite welded joints, I can conclude that the single lab shear test is a very valuable, easy-to-use tool to assess the quality of the welded joints. However, in order to provide an answer to the research question at hand, one must consider how the specific characteristics of the welding process and those of the welded joints it creates interact with the particularities of the single lab shear test. Also, how that interaction ultimately affects the strength values one gets from the tests.
Thank you very much, Irene. An extremely interesting paper on the joining of polymer composites. A question. The mechanism of adhesion of interdiffusion requires that a certain length of polymer chain from one side of the interface diffuses across the interface and penetrates into the polymer on the other side of the initial interface. Have you any idea at all of the lengths of the polymer chains that are needed to interdiffuse in order to obtain a good level of toughness?
Well, I don't know exactly the length that needs to interdiffuse, but what I can tell you is that we have an upper limit for that. So the thickness of the welded joint, the thickness of the weld line is normally around 80 microns. So what I can say is that they won't interpenetrate more than that. That's all I can say.
A question for Alois Ivankovic at University College Dublin. Did you try standard composite fracture tests such as the DCB, the fixed ratio mixed mode test, and the end loaded shear, which will give you mode 1, mixed mode, and mode 2, of course? Did you try any of these tests on your particular joining technique?
Yes, so we did. Several years ago, we were trying DCB tests on resistance welded joints, the ones that have a metal mesh in the weld line. And the interesting thing was that we were no longer able to put the initial crack in the center of the coupon. It had to be either above or below the heating element, the metal mesh. And that actually had an influence on the results of the tests. So we basically stopped that. With other welding processes, for instance, ultrasonic welding, it is very difficult to create a welded joint that is big enough to be able to comply with those tests. So we decided to invest our energy on actually developing a continuous ultrasonic welding process first. And I think in 2 years' time, we'll be ready to create DCB specimens.
An intriguing question from John Allen Pascoe. If the lap shear strength does not increase after a certain point, does it really matter that the full area is not welded?
I guess in terms of strength of the structure, it wouldn't matter. However, I don't think it would pass NDT analysis or NDT. So in that sense, I think it does matter, yes.
Thank you very much indeed, Irene. Thank you. Fascinating talk and technique. Thank you much indeed.
Thank you.
We now go to Kevin. I think we're going to hear a little bit more about lap joints. I think Kevin has strong views on lap joints, so we look forward to Kevin's talk.
That was a great presentation on new experiments cracking welded composite sheets. Now I want to try to remove errors from fracture mechanics for this test. We must use the Griffith energy argument and apply his conservation theory. It's a simple test. You take the two sheets, overlap them and weld the surfaces together, and then you apply the tensile forces here and here. The problem is that the stress is not usually uniform across the joint. Also, the joint is brittle and cracks. A typical force displacement curve can look like this. It's elastic and then goes bang. It's not shear, it's cracking. Now that carbon fibre aircraft parts are being made by welding carbon fibre sheets, there's a danger that cracks can run through the welds at low energy, with disastrous effect. Another Liberty ship disaster may follow this ASTM standard. There's a long history behind this lap joint crack test. Originally, it was described in Phil Trans during 1850 to understand how riveted iron railway bridges failed. William Fairbairn proved that the joint deformed like this by bending, then cracking the rivet. In 1974, I showed with rubber strips that the joint does bend slightly and a low angle peel crack goes through the lap joint. It's definitely not shearing. The stress analysis for the joint was done 82 years ago by Volkerson, showing very high stresses at the corners, as you'd expect. But why did Volkerson not apply Griffith's energy argument? It was 18 years after Griffith. Most engineers still wrongly believe that the strength argument applies. No, when cracking occurs, you must use the energy argument. The energy analysis is easy if we consider a long half joint like this with one crack. The main energy is in the elastic stretched sheets. At the crack tip, the energy is constant as the crack runs along, and so it disappears. It can't drive the crack. There is no stress intensity factor. The Griffith argument leads to this simple result, and the equation has the same dimensions as the Griffith equation, but completely different behaviour. The theory shows that it's not shear. Also, the crack tip does not drive the crack. It's not c to the minus a half. You may find it surprising There is no stress intensity factor. The crack goes at constant speed, unlike the famous Griffith crack, which accelerates. Moreover, the force is not proportional to the joint area. The joint gets weaker as you scale up. So strength can be any number you want. Experimentally, I tested this equation with rubber strips by doing a simple peel test to measure the work of fracture. I call this R here because it's not really equilibrium. So it's different from W, the equilibrium fracture energy. Naturally, this must depend strongly on crack speed, so you must control crack speed to get the right answers. Then I plugged the value for fracture energy into the lap equation to compare with the results on lap joints, and it fitted. Because elastic modulus is a big number, it enters the equation, so force increases by a factor of 100 over simple peeling. It is not just one ASTM standard that causes problems. All these ASTM documents talk about strength and shear. They're wrong. The description of the test as a shear strength test is not correct. The important parameter when it cracks is toughness. We need to correct these errors in fracture mechanics. Lap joint strength does not exist because the fracture force is not proportional to the area. It's not shear, it's cracking. The crack speed is constant, there's no stress intensity factor. The strength depends on sample size. Let's correct these errors today.
Thank you very much, Kevin. Kevin and I have known each other 50 years this year, and I've always known that one of Kevin's real hates is the lap joint test. And actually, I fully agree with you, Kevin. I think it's one of the very worst of the commonly used test methods. But an obvious question is, since the force to fracture the lap joint does not rise in proportion to the bonded overlap area, why has it taken so long to accept your fracture mechanics based ideas, especially by industry?
Yeah, it's a great question. I still don't understand it. Because when I first met you in the 1970s, you were talking about peeling and those sort of things. And that's how I started working on peeling at the British Railways, peeling dirt off British Railways rolling stock. Yeah, but the fact is that if you take a sample like this, which is perspex, can you see this possibly? There's a perspex block, and on it, we've got a strip of rubber, with a bit like Alan Roberts rubber, which is smooth, and you then start peeling it off. I think you may be able to see that peeling. Then you're applying a force, and it peels off. And then you begin to think, this force is being applied, but it's not connected with this big area here. So the force and the area simply, there's no connection. The force actually depends on the thickness of the strip. And so that's how I got to thinking about the lap joint, which is essentially just a lower angle peel test. And you're really measuring energy. And so I suddenly realized that the ASTM standards, which say talk about peel strength or adhesion strength, they're really just garbage. And you have to go back and think, we have to change our whole mindset on this. Let's think in terms of energy and then work through to where we get elastic deformations in, say, the lap joint, where the elastic deformation then has an influence on weakening the joint.
Agree with everything you say. Alloys again, mechanics. Alloys Ivankovic, by the way, was a student back at Imperial College, is now a full professor in Dublin. And he asked a raw mechanics guy, and he says, if there's no crack in a lap shear strength, you can't really apply Griffith. But what about a combination of using a critical stress at a critical distance argument, which both Alloys, myself, and people like Thomas Pardone have very much worked on?
Oh yeah, I take the point. And I think everywhere where you have stress analysis, you have people trying to get rid of the singularity and trying to say the stress will do it. But in fact, that's the error that Griffith fell into in his second paper in 1924. You know, there he went back to the stress criterion. He forgot all his great equation from 1920. And it's a great shame because really the two criteria, the stress criterion and the energy criterion, are simply not consistent. Though if you read a fracture mechanics book, you might get a different story. But the fact is, if it's energy, it's energy. If it's stress, it's stress. But of course, to calculate the energy, you've got to work out the stress. So the things are connected, but not the same. Does that make sense?
It does indeed. We've got to move on, but I can't resist just a comment rather than a question from a very good friend of mine and colleague from Imperial. You know very well, Kevin, Professor Neil Alford. Neil Alford's comment says, ASTM test garbage. I love it.
Well, I think we've gone through, we've gone through a Galilean period, haven't we? I think we're still in the Galilean age, and it's difficult to get rid of these things. And there is some merit, as I think as Irene said in her test on the aircraft, it's a useful test. Everything's the same size, and you're comparing like with like, so you get some relatively interesting information, which helps. But I wish you'd showed more of the stress strain curves where you can see the energy, because they're still brittle, those joints. And if you're on an aircraft with those joints, I wouldn't ride in it. The thing would go bang, really. So you've got to do the stress strain, and then you've got to have toughness. That's my personal belief. What do you think?
I think we should end there, Kevin, to keep us on time. But thanks very much for
thank you.
A great fun talk as always, and thank you for the questions. We're going to move on to the general panel discussion now. So please keep the questions coming in on Slido, and if you can make them more general, then we can address them to more than one person. And the panel is going to be all of our speakers who you've heard from, and also joining us is one of the organisers of this event, Professor Bill Clegg from Cambridge University. So the speakers and Bill make up the panel. Maybe I can pose a first question that we've had in. It's from Professor Russell Morris of Edinburgh University. Slightly long, but I'll try and abbreviate it. The Royal Society is about to publish a report on animate materials. Animate materials are defined as the next generation of materials that are active, adaptive, and autonomous. That is, they exhibit the type of properties that living systems display. And he gives examples from biomaterials that sense and adapt to different situations in the body, to new types of sustainable materials that are even programmed to disassemble once their working life is over. If that was a plane, I hope it doesn't disassemble too early. The question he asks is whether it's likely that the toughness of a material can be tailored to adapt to the environment of the material, especially if there are multiple possibilities open to it. Maybe I'll address this to Rob, because Rob's done a lot of work on biomaterials and toughness. Rob, what's your thoughts on that question, please?
It's an interesting question, having not read the report.
That report hasn't come out yet, so
exactly, yeah. So it's a little difficult to comment too closely, but these notions are not impractical. That we have materials now that disassemble. You just think of certain implants that dissolve in the body when the time is over, and so that's not an unusual concept. But I think trying to emulate what nature does in terms of smart materials or adaptive materials, I think is a very good forward-looking approach. This adaptive structural reorientation, which I think your question mentioned, is seen in a lot of materials like skin. I talked about skin, but in fish scales, where you have a structure in fish scales which has a Bouligand structure. It's a spiral staircase of collagen fibrils, and under load, these fibrils will rotate. We call this structural adaptive reorientation to carry more of the load. So these materials, like a fish scale, will actually adapt to the loading consideration such that it can behave in a tougher fashion. So those are things that we know about. Whether we could ever build such materials into synthetic ones is a challenge, of course, but I'm sure that will happen. One of the biggest problems of trying to emulate biological materials is making them, of course. We make things top down. We take a bit of metal and we beat it to shape and machine it, whereas nature builds from atoms and molecules and builds up. And I think that's something that perhaps 3D printing will provide in the future, that we will be able to make these kind of materials. But I think these ideas are very feasible, and nature's been doing it for eons, of course.
Any other members of the panel? And I think Bill's there. Have we got Bill joined us by now?
I want to add something to the topic of smart material.
Of course, Angie, yeah. Please come in, yes.
So in the cement, actually, in the field of cement, there's a lot of talk about self-healing materials. And the idea actually is to be, one way of doing it is to embed bacteria and using microbial-induced calcium carbonate deposition. That way, if there's a crack in the cement, then the bacteria are going to sacrifice their shell to be able to generate and precipitate calcium carbonate that is going to plug the crack. And this is going to result in a stronger material and a tougher material.
Thank you very much. Other comments, other people? Kevin?
Yeah. Can I say a few words? Because I've worked for many years in the new materials industry, in the chemical industry, for example, and new materials keep cropping up. And as you know, in the 60s and 70s, polymers were the main new material. Now we're trying to get rid of them because they're polluting the planet. But the real point was, all these thousands of new materials emerged, only a few were tough, like nylon or polyester. All the rest are no good, except for perhaps for perspex, which cracks a little bit, but it's still better than glass. So many people invent these new materials, and I hope the Royal Society report goes into this. But the question is, toughness is generally the last thing they consider. They're looking for some functionality. It's transparent or it's electronically active. But very, very rarely do people consider what happens when you drop it on the floor. And it's no good. So that's my point. The great new materials are they're fabulous, but you really have to start considering toughness much earlier in your development procedure.
Other comments, please?
Yeah, hi. I would like to add the comment on, particularly on when you're looking on for biomaterials, say colloid suspensions like emulsions, and always there is a key role to play, a nanomaterial binding a lipids or say a PLA. So it's always the activity, the mesoporous or nanoporous materials depends on orientation of the nanoparticles within the colloid strength. So it has a clear role to play, as already described previously on the self-healing cement. I'm looking at even materials on the biomaterials, bio-waste product in the future, where you can improve the strength of the material of plastics.
Could I add something, please?
Yeah, Payal, please join us.
Actually, there was a recent Nature publication and which described that waste high-density polyethylene could be converted into multi-wall carbon nanotubes just by microwave heating it. And they were so such type of waste material, because it was, I think, topic of Anjay as well as Siva. So you both had similar topics. So such waste plastic then could probably be used into strengthening any of the cement, or probably for your application as well.
Yes.
Because my I think genuine interest is about introducing sustainability in material. So I mainly now I would be looking at how we can do the life cycle analysis of biocomposites. So we would resource some fibers from somewhere where they're producing biofibers like jute or hemp, and then use some thermoplastic or thermosetting, which are again coming from natural resources, then try to create composites. That's, I mean, the ideal, the project aim. So it's a long way to go. So that's what we are looking at now. So we don't tend to, I mean, to be honest, we should focus more on the properties like toughness, but we tend to look at the sustainability aspect, and we sometimes have to probably compromise in it, but I'm sure nature has everything that we need. So we just need to do the right type of research. So, yeah, that's it for me.
Thank you very much, Payal. Irene, and then I see Rob wants to, but Irene first.
Yeah. Thank you. No, I just wanted to reinforce what Payal said. I really think that this time around we should really not make the same mistakes that we made before. So I wouldn't like to end up with a bunch of new materials that are all smart and bio-inspired, but then they are polluting the planet and we don't know what to do with them. So I hope that we learn from that.
So that's why now when we've designed the project, we are thinking about just do the LCA, how much energy, how much water, how much CO2 emission it happens during the process when you are actually producing the fibers. Are you, would there be deforestation of the land? Would there be more cutting of trees when we are growing the fibers? And then how the process it extends. So we are mainly focusing more on the process of creating those molecules and then producing the polymers and composites. Then we would move ahead with the strength of material, and definitely we just keep keep creating more and more biomaterials, saying that they are biodegradable and composite and biodegradable and biocompostable, but they don't really get recycled or really don't degrade in nature. So that's the main motivation, that we would do the LCA analysis first before we move ahead.
Rob,
just a quick comment. I like Kevin's comment, because isn't that the truth that even after the development of fraction mechanics in the 50s or Griffiths in the 20s, toughness is never taken into, very rarely taken into account in the design of new materials, and even more so is fatigue. Most failures in service are fatigue related, and very, very few materials are ever designed from the point of view of fatigue. They're always designed for strength, and they worry about that later. So I think that's an extraordinarily good point.
Right.
I wanted.
Yeah, Angie, come in, please.
Okay, sorry. No, I wanted to add something on what Payal and Siva's point. So I like Payal's idea of just like focusing on sustainability. And in my lab, actually, we're taking one step further and thinking of just building this circular economy. So one of the areas that we've been researching is how do we recycle cement itself? Because when you think about, you build cement, but afterward, at the end of the structure, if you have a natural disaster, what happened to that cement? A lot of time it goes to a landfill. So we've been kind of researching ways where we can reuse the same cement to produce new cement. That way you really have a full circle. And going back again to Siva's point, is we realized that just like in biological material, we really have to engineer from the bottom up. We have to look at the nanostructure. And one thing that we've been seeing is that using nanomaterial, carbon-based nanomaterial, we are able to toughen the material at the nanoscale by reducing the porosity and making sure that we can activate this multi-scale toughening mechanism, going back again to Rob Ritchie's point, and trying to just having this suites of toughening mechanism from the nanoscale up to the microscopic length scale to yield a tougher and more sustainable material.
Excellent.
We've got a good number of questions coming in. What I'll try and do is to group them together so we get a theme going rather than going from A, B, and all over the place. One thing that as a question that's sort of come in is that really, with a few notable exceptions, the methods of fraction mechanics do not seem to be used extensively in engineering design applications by industry. Any comments, please, on the reluctance of many industries to adopt fraction mechanics for design and for material lifing? All right, Rob first, because I know Rob is a consultant to several companies on this.
I think that's changing, though, quite frankly. I mean, I think from the last, it took 1970s before the US Air Force used fraction mechanics in the design of airplanes, and it took another 20 years before it hit commercial aerospace as well. So I think things are changing. I see fraction mechanics used in all sorts of applications, in the bruising of fruit. Your colleague was working on cheese, wasn't he? Cutting of cheese and so forth in Reading. So there's lots of applications that are happening. And so I think things are changing. What is not used, though, is in the design of materials. I think, you know, the choice of materials. Most designers still want ductility. In their mind, they want that parachute, that ability. If something goes wrong, the material will still fail gracefully. So a lot of this, so I think the application of some of the more modern, higher strength, perhaps more brittle materials has been delayed. They may have good toughness, but if they don't have enough ductility, that's inhibited their use. But I think now we have ceramic composites in engines and so forth. These are nominally brittle materials, but they have some ductility. I think things are changing. I see fraction mechanics being applied more and more in different industries.
Kevin, did I say you wanted to come in?
Yeah, it's really an interesting question. I used to work in industry, and I was around in ICI when they invented PEEK, which is the material going into these plastic composites that Irene mentioned for aircraft. And there's a fabulous sort of material. But when they started testing it, they were using the old metals testing protocols, which is quite amazing because the things sort of delaminate. They just don't fall apart in the same way that a metal would. And so it's really quite bizarre. And so you go along to them and say, please, why didn't you test it in a bending crack test or put a huge crack in it and do something different? Because they very rarely were used in pure tension. They're usually bending or they're under some hoop stress or some pressure in an aircraft. So it seems to me that because the training and the standard tests have not kept pace with the new materials developments, there's a bit of a gap in industry. It's changed a lot now, I think. So the industry's caught up a lot. But to give you an example from the old days in plastics, we had these plastics like polythene. You couldn't break it. You could stretch it. You just kept on stretching, like the skin that Rob mentioned. So to actually do a fraction mechanics test, you had to put a huge gouge in it with a razor blade to get any crack at all. So you suddenly realize that these new materials have to be treated in quite a different way from the standard metals test. Do you not think?
Angie,
Yeah, I wanted to add something to that. That's a great point, Kevin. I think another reason why right now the industry hasn't adopted fracture is because it's very difficult to be and very expensive to be able to test using the standard method. Because the classical ASTM method, to be able to have it, if you want to have the dimension greater than the fracture process zone, you really need to have a huge amount of material. And when you think of material prototyping, a lot of time we're not there yet. And it's easier to do, for instance, a uniaxial compression test than to go and have a compact tension test in this case. And also sometimes we not decide a lot with our cement nano composite and rock specimens. Sometimes the specimen is actually even so fragile that it's going to break just by machining it. When you're trying to machine it to have a standard 3-point bending or compact tension test, it's just going to break already. So this is what is really good, what we've done in my lab, to be able to develop the scratch test, where you need just a small amount of specimen, just literally, it could be a cylinder 1 centimeter tall, 1 centimeter wide, and from this you can probe the fracture toughness. And what we really hope is that those methods will accelerate the adoption of fracture as a criterion for materials design.
Can I interrupt a second there, Kevin? Just that to take this further, we have a couple of questions here on this. Mark Gessing comments and for your attention, fracture toughness is different from other material properties such as density, elasticity, modulus, or Poisson's ratio, because it's not independent of the sample shape or loading. This leads to some of the difficulty in using toughness-based criteria in material selection or engineering design. Now, I know, of course, in the various standards, we try to define K1C and G1C, which is plane strain typically for LEFM, and therefore overcome that. But I think it's an interesting point that Mark makes. Would you care to comment, Rob?
I mean, I think this is the inherent problem with fraction mechanics, that if you're measuring something like K1C, then that's pretty robust generally in terms of the initiation toughness. But Joe Gallagher once said, if you can measure K1C in a reliable fashion in a material, you probably don't want to be using that material because it's basically, you have to be high strength and low toughness and not too much plasticity. And that's the issue, I think, that you want materials to be on an R curve. You want plenty of plasticity, and that makes them very, very difficult to measure. So a lot of fraction mechanics is abused, and it's just almost natural it happens to be that way, because the materials you want to use will not fall in that category of K1C generally. So I'm a strong believer of getting materials on a rising R curve. But in terms of robust and sound fraction mechanics, you're on a little bit of uneasy ground there. And there are things like specimen size and specimen dependent issues that you have to worry about. So it's a very, very good point. But I think we've taken care of a lot of them now through the standards and the development since the last 30 years or so, that I think it's more robust than it used to be. But there is that inherent problem with the methodology.
I just comment, even with composites, which have come to the party, of course, much later, our TC4 committee, which have developed the standards, which now are ASTM and ISO for doing G1C of polymer fiber composites, there we say we concentrate on initiation. Whatever we know likes this industry is that rising R curve you get from fiber bridging, etc. Because even though they might use the G1C initiation value for selection, and maybe even some service lifing, as you say, Rob, they know they've got the insurance there of the rising R curve in practice. So I think that's a wonderful comment. Kevin.
Yes, I'd like to pick up Professor Okono's point, because it's a bit like when the metals were in the infancy in the 19th century. The indentation tests, like the Rockwell, the Brinell, those things, they took off because you could actually get a good estimate of, say, the plasticity of the hardness, and even cracking with a very small test, which didn't do much damage. And I like that. I think the scratch test is the one that's coming, or even a cutting test, where you suddenly can see the effects of toughness on a small scale, not with big equipment, get a reasonable quantitative answer, and do it anywhere, out on site, for example. But do you not think that they need these smaller tests to get on-site information without having to go into a lab and get lots of elaborate stuff like that?
I think the problem there, though, Kevin, is that is to get this value, which is independent of the sample geometry. And therefore you have a value which can be measured from laboratory to laboratory and within certain specifications. Irene, did you wish to?
Yes. Yeah, so two things. So I actually support this idea of let's make specimens smaller and that are easy to weld, so that we can actually do some studies of fracture propagation, crack propagation, instead of just single lab shear testing. That was the first thing. And the second thing is that, unfortunately, I'm going to have to leave because I planned my calendar today based on the original schedule. I'm really enjoying this. I'm super happy I was invited to be part of this. And I just have to say goodbye.
Thank you very much, Irene. Tremendous contribution. Thank you very much. Look forward to seeing you in September next year in London.
Oh, yes. See you there. Definitely. Bye.
As a follow-up question to this, Mark Giesing again said, what is the panel's take on damage mechanics approaches as an alternative approach to fracture mechanics? My personal view, having recently got deeply into this subject and published on it, is that I think with damage mechanics, you certainly need to know the answer before you do your modeling and prediction. But what do others think? Bob? Yeah, sorry, Bob. Yeah.
I mean, I think that's a good point, but I think damage mechanics often is better applied to materials that fail by distributed damage rather than by a single dominant crack. So there are certain applications where damage mechanics is much more powerful. And when you're talking about metal fatigue or something like that, then a fracture mechanics approach is often, because it's a single dominant crack approach, is much better. So I think these are two parallel techniques. They're different. But I think they have their role in specific cases. The only thing with damage mechanics to me is, though, that you're right. You almost have to know the answer, and they tend to be rather arbitrary. There's a few examples where the physics has been put in, but they, in many cases, seem very arbitrary to me. But they provide a means of predicting, a nominal failure. So I think they have their place, definitely.
Any other, Kevin?
Yeah, I'm always interested in concrete, reinforced concrete, as an example of that procedure, because obviously any engineer is designing a bridge, like the Genoa bridge that went down a couple of years back. You presume that the concrete is totally riddled with horrible cracks. And so then you start thinking of the backup and how much steel you put in and where you put it in and how it fails. And so that is the most competent method for avoiding these problems. And that is why the Genoa disaster is an example we've got to study, because something obviously went wrong there. So the materials got defects. It's crumbly, it's not got a high fracture toughness. It's already failing in part and the damage is in there and that will only develop. So you need the backup system which the steel structure is providing. Is that not the right answer?
Nobody seems to want to answer you. Siva, please come in.
The early days accidents, it's already causing again the permeation of water and the corrosion. So that has been very nicely addressed by Anja's self-healing mechanisms. When we are using already nanomaterial, the permeation is not reaching to the steel. We are already addressing the issues which can cause the safety point of view. So that's a multi-approach. I think the steel will be used to give the long-term protections, but the length of the accidents is we are delaying it through the mechanism that we are using nanomaterials.
So we move on. I think from a knowledge of the toughening mechanisms, major improvements have clearly been made in increasing the toughness. For example, in my own area of structural adhesives, over the last decade or so, we've got G1C up by a factor of 50 in structural adhesives. They've gone from being the brittle two-tube aldehyde epoxy that we know to actually bonding the modern Formula One cars. And to my knowledge, even though the composite may shatter, which it's designed to, of course, absorb energy, no adhesive joint has ever failed in any of the accidents you see on crashes, etc. So we've done tremendous things there. But do you think we can continue this trend without discovering new toughening mechanisms? Do we need to find new ways of toughening materials before we start getting an even further increase in developing material toughness? Or is it just empirical science? Kevin, you think you?
Well, I think Angus' talk is an example of that, because you have a material, you know it's very brittle, you know it can fail catastrophically, and so you put in then some nanoparticles, and that can increase it. I think empirically, that's been known for a century with toughening of rubber, for example, or toughening of crazing materials that you've worked in the more polymer areas. So you know it works. So why not just push that through to the logical conclusion that all materials should be potentially toughened by these methods? So you really have to just press on, even though it's slightly empirical. You might not understand fully what's going on, but you can get improvements by an order of magnitude, 2, 3. I remember working in cement. I'm showing you the cement spring here. Now, this is one that Neil Alford worked on, who talked earlier. All you do, you put a bit of polymer in, get rid of the defects, and suddenly it becomes tougher. You can make a spring. So cement, you couldn't even make that of ordinary cement. But the fact is, the toughness improves by getting the porosity down. It could be 2 orders of magnitude higher. And then Neil Alford put some fibers in. It went up by another 2 orders of magnitude. So there's a immense potential, I think, for increasing the value of toughness.
Rob.
Yeah, I was just thinking that what you described for the polymer composites, there was a similar burst of activity with ceramic composites, mainly headed by people like Tony Evans, who increased the toughness of ceramics from single digits like 1 to 2 to 3 up to the 15 or 20. And I thought that was a major achievement in increasing toughness. But there is a backstory to that, is that when you generate these high toughnesses, that was done by shielding, basically, as I talked about, bridging or phase transformations. These materials became susceptible to fatigue now because you had some inelasticity generated. They no longer had a linear stress strain curve. So those toughened ceramics actually de-toughen under cyclic loading, to put it in a simple way. So I agree that there is plenty of upward mobility by putting together composites at many different length scales, but sometimes that leads to other problems. And I think the fatigue of a toughened ceramic is one such example.
On this theme, Etienne Bartels asks, in glassy polymers, there's typically strain softening and then hardening at larger strains. And she asks, is there a clear understanding what the impact of this dual behavior on toughness really is? In other words, how much softening do we need, or will softening kill the beneficial effects of the later strain hardening? So I guess the theme here is really to develop these new tougher materials. Is aiming for a specific type of stress strain curve by some type of controlling a microstructure needed?
It will certainly make the measurement more difficult, I think. You know, in materials that do show strain softening, if you try to use conventional fraction mechanics, nonlinear elastic fraction mechanics, use things like J approaches, they just don't work very well because they have to have a small zone of hardening at the crack tip. So we've seen this in metallic glasses, which strain soften initially, and the numbers that you measure just are so dependent on every variable imaginable. It's very difficult to get a single number.
So no clear-cut correlation between the strain softening, strain hardening, and G1C or K1C or J1C.
I haven't seen that develop yet. So.
Kevin. Yeah, but the great thing about polymers, and you're an expert on, I think you've written a book on this, Tony. That you get this.
Thanks for the advert, Kevin.
But you get the popcorn effect, where suddenly it cavitates, and then you get fibers form. First it goes softer with the popcorn, and then as you stretch the fibers, it gets tightens up again, and so you get this crazy thing, which can certainly give 2 orders of magnitude increase in toughness. So that's a very curious effect. I think in metals, when the holes open up, unfortunately that's very damaging, isn't it? So the pores suddenly grow and they're not and don't tighten up. But in many biological materials, you get this the cavitation and crazing sort of effects, and we all know that putting nanoparticles in can promote those activities. So that's a key area, I think, for coming up in, say, the Professor Bartel's area.
Well, on the same theme, a question to Angie from Leslie Banks Sills, and she says, what happens if you increase the volume fraction of the nanocarbon material in your cement? What happens if you go to 1, 2, 5%, for example?
That is an excellent question. I mean, 5% is the holy grail. If you were able to achieve it, that would be awesome. But right now, the issue is really the dispersion. So you're really going to have those clusters. I think right in my lab, we've been able to go to 0.5%. In the literature, the limit right now is 0.1% to disperse it in general. Because if you go to 1%, then you start having those clusters. And when you have those clusters, they're going to behave more like rigid inclusion. And then you also have an increase in micropores. So what you see actually is a decrease in the toughening and the strength of the material, because you have the micropore, and you're no longer activating the strength, the toughening effect of the carbon fiber or nanomaterial, because they are clumped together. So that is one of the challenge right now. And the point of the science is to try to find ways to continue to disperse high volume fraction of nanomaterial within Portland cement matrices.
Siva.
Sometimes the packing density, for example, I think Ian Kinloch has done a really good work on a composite, for example. He has demonstrated in a size and the loading playing a key role to get the maximum efficiency, the size of the material and the loading, because you are enabling the packing density and the interface between the fibers and what you are putting it, same as in the concrete is as well, the porosity. How do you enable the porosity mechanisms, and what is the volume, a void you wanted to fill it in order to maximize the permeation path? That's play a key role.
We have a general question, really. I guess the theme really is there still future scope in alloy design to make tougher alloys, or is that now a subject which is we've reached as much as we can in that area? Rob, this is probably for you. Maybe Rob first.
Yeah.
I think that the toughening of metallic materials and alloys has just had a burst of activity in the last 10 years. And there's been 2 approaches. One, the one I mentioned, which is high entropy alloys, which is the multiple principal element materials. Most of metal alloys have a single dominant element, like iron in steels or nickel in superalloys. Now multiple elements have been put in, and there's just simply millions upon millions of potential materials out there, and that's had a lot of activity in the metallurgical field. Most of them have not been particularly good materials, but some of them have been outstanding. Some of the ones that I mentioned on chromium, cobalt, nickel based have just amazing properties. But that is a very expensive route to add all these complicated, these expensive elements. And the other approach is to use pure metals and to develop properties the way that nature does, through developing gradients by thermomechanical treatments and the like, and building up gradients in grain size or hardness and so forth. And that's clearly cheaper in terms of material, but then you have the processing difficulty of how you create those gradients. And so that's in its infancy too. But both those approaches, which are very distinct, I think have the potential for generating lots of new important alloys. In the high entropy ones, we now have much better cryogenic materials than we ever had maybe 20 years ago. And I think there's an opportunity in high temperature materials with what's called refractory high entropy alloys. That there's a lot of work there. Most of these materials are hopelessly brittle, so we don't know yet. But I think there's a lot of future in metallic alloys now with those two very different approaches.
Kevin.
Yeah, I was maybe next year. I was hoping Rob can give us a talk on the history of the single crystal turbine blade, because I've been trying to find out toughness values, but it never seems to crack. Is that true? Because it's obviously been designed that it lives a long time in very harsh environments. But it seems to me that's a good example of what Rob's talking about. That here's a very special material which has wonderful properties. Very rarely, if ever, cracks, and we need to design more alloys of that type.
Yeah, well, I mean, I think that's why I don't like nanomaterials, because single crystal turbine blades are the ultimate in that regard. But they do, one of the issues though that's happening now is that these materials like single crystals and nickel based and now ceramic composites have enabled the temperature of engines to increase, which is very good for their efficiency. But what it's led to is increased problems with corrosion, oxidation, and sulfidation problems. And you probably know Rolls-Royce has had a big problem with their Trent 1000 engine, which is a single crystal turbine blade with terrible sulfidation cracking in the lower portion of the blade. And it's simply due to a strange combination of the elements in the alloy and the particular atmospheres that some of their engines go through, particularly when it's salt and sulfur. So these are the big issues. So single crystal turbine blades crack, there's no question about that. Fatigue is the one that does it though, rather than pure creep. But the oxidation, sulfidation problems are going to become much greater now because of the higher temperatures that these engines run at. So this is the new normal, in my opinion.
Our colleague who made the ceramic spring, my colleague, particularly Imperial, Professor Neil Alford, asks, he says, comments that fibre pull-out tests to determine fibre shear stresses are very tricky. What does the panel think about their usefulness in predicting, I guess, and therefore improving the properties of fibre composites? That's fibre pull-out tests. Are they useful to us? Kevin, Rob?
Yeah, well, yeah, I came into that quite a long time ago, I guess, as most other people did, because when the composites were really picking up in the carbon fiber era in the 1960s, 70s, and so on, it's obvious that the fibers were bridging the cracks and the gradually being pulled out, and the nature of that pull out was very significant. And at first, of course, it was interpreted in terms of fiber strength and the strength of the interface, the weak interface. And I think that may be a little bit naive when we look back. Maybe Rob can comment on that. But I think those ideas about the interface and this fiber pull-out have improved immensely, especially with Raman spectroscopy, what's going on in the molecular level. And so I think times have changed. We have a more mature impression of what's really happening in this fiber pull-out. What do you think, Rob?
Well, I think, I mean, I not talk directly about the fiber pull-up, but I think in general, the complexity of the materials that we're now talking about, which tend to be multiple length scale composite type materials, makes the topic of fraction mechanics very difficult to utilize in its form that we know it today. And I think that's why damage mechanics has become important. But you look at that silicon carbide material, it's very difficult to use fraction mechanics on that, where you've got cracking forming in different parts of the material, and as you point out, there's cracks there initially and so forth. It is distributed damage. That's what you'd really like. It's much better than a single dominant crack. So I think these issues mean that the tests that we've conventionally used to measure the toughness of metals are just not going to be good enough for some of these complex things. And I think the fiber pull-out test is one such thing. It does define something useful. You can see whether you've got the behavior that you might want, but as a design tool, I think it's very, very difficult.
Kevin?
Yeah, I'm very interested in this because way back we're doing sort of model tests with rubber and pull-out, and it struck me that really when very smooth surfaces, especially at the nano level, the cracks open up as it's pulling out and then they heal again. So you get this peel and heal, which gives a stress whitening rather than a sort of total separation. And so people have not used the Griffith concept properly, which is really a peel and heal concept. The cracks should heal up, shouldn't they? For God's sake, the cracks have got to heal. It's in equilibrium. And so if this can happen at the nano level, surely that will have a great influence on that sort of pull-out concept.
Siva, did you wish to make a comment?
I just want to come back earlier discussion regarding alloys and application. I think the alloys certainly have a huge role to play from feature hydrogen economy and feature how do we improve the decarbonization role. Whereas same as in the fiber, what we see here is the lightweight of feature planes when we are discussing, and particularly have a greater role to play and optimizing the testing with what we have discussed critically about ASTM standard, as well as fiber, particularly the dispersion technology, because we are dealing no longer with the simple carbon black. It's no longer spherical particle platelets. So wetting and interfacial adhesion and alignment playing a key role on the performance and the right loading. So we really looking forward that get more strengthening further into the near future.
Yeah. I think we've got one interesting last question before we bring this question and answer session to an end. It's from a colleague, Professor John Deere at Imperial, and he really says, in the light of the comments from Kevin about the ASTM lap shear test, which is so widely used in the aerospace industry, and fabrication bonding, are composite fuselages safe?
Well, yeah, obviously the composite plane is the greatest invention of the last 30 years, I think, and it will continue from strength to strength. Yeah. They're much safer, much lighter, much easier to control and optimize. I think it beats metal hands down, but then again, I'm not a metallurgist, so maybe some people would argue with that.
Well, to give my colleague John and any other people in the listening, etc., I would point out that even though I'm an adhesives enthusiast, that adhesives are not used to join primary aircraft structures in civil aerospace. They are banned from being a primary structural joining technique. And that's why you see all those titanium fasteners when you look down the fuselage wing of a 787 or A350. The adhesives are only used in secondary structures, which are not critical to the safety of the plane. So if that gives you a bit of better feeling.
It did work on the Mosquito, didn't it? And the Brits were pretty good at sticking things together with all sorts of gunge.
I did say civil planes. I did limit my comment to civil aircraft. On military aircraft, they are used in that role, but not on civil aircraft.
Right, but that must change surely with experience.
I always tell my students now that with plastic airframes and ceramic engines, maybe it's time to take the train.
I think on that comment, we must end the discussion. Thank all the panelists, speakers, and all the audience for sending in such great questions and making this such an exciting question and answer session time. When we started planning this meeting, we were very worried that after 2 minutes we might have nobody listening, but that's not at all the case. So thank everybody, and we will conclude now with a very short conclusion from Kevin, just a few minutes of conclusions.
Well, it's time now for conclusions. I want to thank all our speakers and thank you in the audience for your great questions. And now we can look forward to next year's 2021 meeting in London at the Royal Society. The main points today, I think, are these. First, cracks are very important, especially if you're flying in an aircraft. Then, much research is still proceeding. For example, on graphene production or on reinforcement of materials to inhibit cracking. And finally, confusion still exists between strength and toughness a century after Griffith. But there is no doubt Griffith got it right with his conservation energy theory of cracking. However, his famous equation for a stretched sheet is only a particular solution. It does not apply generally to many crack configurations. For example, the rubber sphere adhesion crack from Alan Roberts, or the disc compact test is quite different. And also the lap joint test may look similar in dimensions, but is very different in behavior. And we need to correct errors in fracture mechanics. First of all, there's a size effect, which is not mentioned in fracture mechanics textbooks. Also, stress intensity factor does not exist for many cracks. For example, a lap joint crack or a peeling crack. And finally, energy conservation must be applied, and people have failed to do that in the past. The stress balance, although fascinating mathematically, is not sufficient. And finally, thank you all for attending this web broadcast. It's now time to get back to do new science during lockdown. Galileo's original fracture mechanics book was written under lockdown. Of course, he was under house arrest at the time. And my work from home project has been a new book on crack control, which will be coming out soon from Elsevier. Good luck, thank you, and goodbye.